Good afternoon, students. You welcome to this online class. In today's class, let us see the hydraulic turbines. What are the hydraulic turbines and how does they works? What is the main use of the hydraulic turbines and what are the construction details of the hydraulic turbines? These are the topics. Let us see in today's class. First of all, you have to understand about the power generation. In India, the electricity is generated from the thermal resources such as the coal-based power plants and by using the water resources, the power is generated and by using the some renewable resources also, the power is being generated. But one of the greatest advantage of using the hydro resources is the efficiency of the hydroelectric plants is very high. Because of this, the in government, the government is focus more on hydro resources. There is a ecological advantage. Next, the conversion efficiency of hydro electric power plants is high. Because of this reason, there is a more focus on hydroelectric power plants. Hydroelectric power plants are nothing but using the water as a resource. The mechanical energy will be developed from the mechanical energy. Using the electric generator, energy is converted from mechanical to electrical energy. That electrical energy is supplied to the domestic and industrial use. If we come to the hydroelectric power plants, one there is a huge demand for hydroelectric power plants, and in India there is a more potential for hydroelectric power plants. 148701 megawatts is the hydroelectric potential in India, but 46,000 megawatts power, that is the 12.3 percentage of the total power generated in India is from the hydroelectric power plants. So there is a huge gap between the potential and the current existing electric power plants. So there is a more demand for hydroelectric power plants. In fact, in hydroelectric power plants, the hydraulic turbines are used to convert hydraulic energy into mechanical energy. So hydraulic turbines plays an important role in converting the mechanical energy to electrical energy. The generators are also mounted on the same shaft of the turbine, such that the hydraulic turbines will convert hydraulic energy to mechanical energy. Then, by using this mechanical energy, the mechanical energy is converted into the electrical energy by using the generators. So the one of the basic thing a student has to understand is what is the function of a hydraulic turbine. Hydraulic turbine main function is it will convert hydraulic energy into mechanical energy. There are the other type of hydraulic equipment called pumps. The main function of the pumps is which are used to convert mechanical energy into hydraulic energy. For example, in order to lift the water from the ground level to the tank level, the pumps are used. So the pumps are called they are the hydraulic machines. So hydraulic machines are of two types. One is hydraulic turbines. The second one is hydraulic pump. Both together can be called as the hydraulic machines. The turbine will convert from hydraulic energy to mechanical energy, but whereas the pump will convert from mechanical energy to hydraulic energy. Both together can be called them as hydraulic machines. Because of the huge potential, next, the demand for hydroelectric power, the government is focusing more on the hydroelectric power generation. That may be from the very big plants or from the small size capacity plants in various ways. The government is giving more emphasis to harness the power from water resources. With this background, let us go to the hydraulic turbines. Let me share PowerPoint presentation. Okay, as per our earlier discussion, the hydroelectric power plants are having the huge demand. So let us see the various components in hydroelectric power plant. This diagram shows that there is a reservoir, The dam is constructed across the river in order to store the water in the reservoir. So here the basic function of the dam is to store the water. The stored water is conveyed from the reservoir to the hydraulic turbine. So here there is a wheel. This wheel is rotating in anti-clockwise direction, and this wheel is having the buckets to supply water to the turbine. Water is conveyed from the reservoir to the turbine using penstocks. The penstocks are the large diameter pipes which are basically used to convey the water from reservoir to the turbine. The arrow marks indicated here represents that the water is conveying from reservoir to turbine. If you look at the exit of the penstock, this pipeline is called it is the penstock. Generally, the concrete or the steel are the materials which are used for penstocks. The penstocks are the pipelines in actual hydroelectric power plants. The diameter of the penstock will be around 8 meters because more quantity of the water it has to be conveyed from reservoir to turbine. Therefore, the larger size pipelines are used. They are called penstocks. Next, at the exit of the penstock, there is a nozzle. The nozzle is nothing but the decreasing area duct is called a nozzle that is fitted at the exit of the penstock. The main use of the nozzle is to convert the hydraulic energy into kinetic energy because the selected turbine is impulse turbine. Impulse turbine means at the inlet of the turbine, the available energy is only kinetic energy. Therefore, to convert the pressure energy to the kinetic energy, nozzle is used. So, from the nozzle, with high velocity, the jet issued from the nozzle directly supplied onto the buckets of the turbine. Buckets of the turbines means in the shape of the cup, the buckets are radially arranged. A series of blades are radially arranged to the rotating wheel. This is called it is a turbine. When the jet impinges on the buckets, then the jet is splitted into the two halves and the jet will follow the geometry of the bucket such that the direction of the flow changes over the bucket. Because of that, it will exert force on the bucket. So, due to this force which is acting at some radius from the axis of the turbine wheel starts rotating. As the wheel is rotating, the water first impinges on one bucket, Next, it moves up, and this next bucket will come and it receives the jet, and after that, the next bucket, and so on and so on. So always there will be a impingement of the jet on the buckets. So that the hydraulic energy is converted into the mechanical energy. After impingement, the water has to collect. The water which is collected after developing the power is conveyed through tail race. So here, from technical point of view, the level of the water in the reservoir is called it is head race. The level of the water in the downstream is called it is the tail race. And the gross head is indicated here. The gross head is nothing but it is the difference between the head race and tail race is called it is the gross head, because while conveying the water from the reservoir to the turbine, there will be some loss of energy, because the length of the pipeline is around 3 kilometers or 4 kilometers is the actual distance of the pipelines. As you know that friction is the one of the inevitable phenomena that will offer resistance to the flow when the water is conveying in the penstocks. Using Darcy-Weisbach equation, the head loss in penstocks can be estimated. Let us say the head loss in the penstocks is it is HF. Small letter H suffix F indicates that it is the frictional head loss. Gross head is nothing but difference between the head race and tail race, and HF is the frictional head loss. If you subtract the frictional head loss from the gross head, the head is called it is the net head. Actually, the net head is the only head available at the inlet of the turbine. Therefore, the we have to see that the net head value should be high. So this is called it is the layout of hydroelectric power plant. Means in layout of hydroelectric power plants, we can observe what are the major components in hydroelectric power plant and what is the function of each component. How hydroelectric power can be harnessed from water can be understood from the layout of hydroelectric power plant. So this layout will give the basic idea how to generate the mechanical energy from hydraulic energy using hydraulic turbine. The hydraulic turbines are classified based on the type of energy at inlet of the turbine. Based on the type of energy, the turbines are classified into impulse and reaction turbines. Impulse turbine means at the inlet of the turbine, the energy available is only kinetic energy and the pressure from the inlet of the blade to the exit of the blade is constant. In case of Pelton wheel, the pressure is atmospheric pressure. So at atmospheric pressure, the high velocity jet comes and it flows over the bucket of the hydraulic turbine such that the hydraulic energy can be converted into mechanical energy. Suppose at the inlet of the turbine, the energy available is it is the sum of kinetic energy and the pressure energy. Such a turbine is called it is the reaction turbine. In reaction turbines, within the turbine, the pressure changes from the inlet of the turbine to the outlet of the turbine. Such a turbines are called reaction turbines. So the first classification is based on type of energy. Hydraulic turbines are classified into impulse turbines and reaction turbines. The next classification is based on the direction of flow through the runner. The direction of flow to the runner may be it is the tangential flow and radial flow, it may be axial flow, it may be mixed flow. Tangential flow turbine, just now we studied in the layout of hydroelectric power plant. We supplied the jet in the direction of tangent to the wheel. Therefore, the Pelton wheel or the turbine which has been shown in hydroelectric power plant is a tangential flow turbine. So it is clearly understand that the jet is supplied tangent to the runner. Therefore, the Pelton wheel can be called as tangential flow turbine. The next is radial flow turbine. Radial flow turbine means from inlet to the outlet of the turbine, the flow takes place in radial direction. Let us say radial in inward turbine means from all directions the water is supplied to the runner such that within the runner the flow takes place in radial direction. Such turbines are called, they are the radial flow turbines. Old Francis turbine is a typical example for radial flow turbine, whereas the modern Francis turbine in which the flow enters radially and it leaves axially. That means 90 degrees turn will take within the runner. Therefore, the type of the turbine is called it is the mixed flow turbine. Means radial inlet and axial outlet in case of modern Francis turbine. Therefore, modern Francis turbine can be called as it is the mixed flow turbine. Next, axial flow turbine. The best example, Kaplan turbine. In Kaplan turbine, the water flows parallel to the axis of the turbine. Therefore, the Kaplan turbine can be categorized as it is the axial flow turbine. So the second classification is based on the direction of the flow through runner. If the direction is in tangent direction, it is tangential flow turbine. If the flow is in radial direction, it is called radial flow turbine. If the flow is parallel to the axis of the runner, then it is called mixed flow means radial inlet and axial outlet is called it is the mixed flow turbine. So the first classification is based on the type of energy at inlet. The second classification is based on the direction of flow through runner. The turbines are classified into different types. Yeah, the next classification is according to the head inlet of turbine. In Andhra Pradesh, there is a Srisailam project and Nagarjuna Sagar. The head maintained in Srisailam reservoir and the head maintained in Nagarjuna Sagar both are different. So high head can be maintained in Srisailam hydro, hydroelectric power plant. In reservoir, due to the topology, depending upon the capacity of the reservoir, practically the high head can be maintained. So the conclusion is from the reservoir to the reservoir, the water level in reservoir varies. Suppose the head maintained in the reservoir is in the range of 800 to 1770 meters, then the turbine which works against such a high head in the range of 800 to 1700 meters are categorized them as high head turbines, whereas the head is in between the 60 to 250 meters. The type of the turbine is called it is the medium head turbine. If the head is less than 60 meters, then it is classified into the low head turbines. So the third point, what I want to explain is, according to the head and inlet of turbine, turbines are classified into high head turbines, medium head turbines, low head turbines. This is about the third classification. Next classification is based on specific speed of turbine. Based on the value of the specific speeds, the turbines are classified into low specific speed turbines, medium specific speed turbine, high specific speed turbine. So this is the fourth classification which we discussed now. If the specific speed value is in the range of 10 to 35, Pelton wheel of single jet is used. If the specific speed value is 60 to 300, Francis turbines are used. If the specific speed value is 300 to 1000, then the Kepler turbines are used. Next classification is based on the disposition of turbine shaft. The turbines are classified into horizontal axis turbine and vertical axis turbine. So this is the fifth classification. So one of the important question is classify the hydraulic turbines. Then you have to explain these five types of classification. So let us see the construction details of Pelton wheel. Here the diagram is a runner of a Pelton wheel. The runner of a Pelton wheel is it is a circular disc on the periphery of which a number of buckets evenly spaced or fixed. The shape of the bucket is of a double hemispherical cup. This is one of the very much important point. The buckets are assembled radially to the disc of the runner. The shape of the buckets are double hemispherical cup. Each bucket is divided into the two halves. This is a disc to which the buckets are radially arranged. Now, let us look at the construction of the bucket of a Pelton wheel. This is the bucket of a Pelton wheel. Here it is having splitter The splitter function is it will split the jet into the two halves. Jet will come and impinge on the splitter. Splitter is nothing but this separation line is called it is the splitter. When the jet comes and comes and it is divided into the two halves because of presence of the splitter. One half will flow over the half of the bucket, the another half of the bucket, the another half of the jet flows. And if you look at the bucket of the wheel, here there is a small undercut. This undercut is to avoid the interference between the jet and next coming blade. Yeah, this is a Pelton turbine. The runner rotating in anti-clockwise direction due to the supply of the jet from the nozzle onto the buckets of the Pelton wheel. The radial vanes are here. Each one is in the form of a cup. Then the jet issued from the nozzle is supplied onto the bucket. So first bucket, after that it passes, next bucket will come. After that next bucket like it and so on. Always there will be the impingement of the jet on the bucket of a Pelton wheel. Because of this, force is exerted by the jet on the bucket in radial direction. In radial direction, if the force F is acting here, this force into radius will give the torque. So by producing the torque using the jet, the Pelton wheel starts rotating with some speed. That is how the hydraulic energy is converted into mechanical energy. There is a nozzle and spear arrangement in the location of the nozzle. This regulating mechanism is very much important to control the flow rate. What is meant by flow rate? That is the quantity of water supplied per second is called it is the flow rate. This can be controlled by moving the spear in forward and backward direction. There will be one hand wheel. If you rotate this hand wheel, because of the screw and nut mechanism, the spear advances and it will come back depending upon the rotation of the wheel. As you know that the load on the hydroelectric power plant is not constant, it varies from time to time. For example, morning time utilization of power is different from night time. So in a day, sometime you need the more power, sometime you need the less power from the turbines. So whenever more power is required, the more quantity of liquid has to be supplied. Whenever you need the less power, then the low quantities of the flows is sufficient to generate the power. So such regulation of the flow rate is achieved by using the nozzle and sphere arrangement. In this diagram, there is a casing. Actually, for impulse turbines, casing is not having any hydraulic function, but it will prevent the splashing of the water, and it will provide safety for the crew they are working in power plant. Because if something goes wrong in such situation, the casing will protect the human beings without causing any accidents. So this is about the casing of the Pelton wheel. Next, let us see what is the use of the braking jet. When the main jet is supplied, the turbine rotates in anti-clockwise direction. But if you want to stop the turbine, then first input energy has to be supplied to be controlled by reducing the flow rate coming onto the bucket of a turbine. Even though the flow rate coming out from the nozzle becomes zero due to the inertia of the rotor, it will continue to rotate nearly half day like that. But in order to stop the Pelton wheel with less time, the braking jet is used. What this braking jet will do is it will supply the water on the backside of the blade. When the water is impinging on the backside of the blade, obviously it retards the rotation of the Pelton wheel. Therefore, to control the speed, whenever you want to stop the train, then you activate the braking jet. Normally, the braking jet is not in use. Only when you want to stop the turbine rotation, then only the braking jet is supplied, that is on the back side of the bucket of a Pelton wheel. So these are the various components of the Pelton wheel, and what is the function of each component has been explained to you. This diagram shows the from the nozzle and sphere arrangement how the jet is coming, how it is splitted into the two halves. And this is a the bucket top view. This is a this line, vertical line is it is the location of the splitter. The jet first comes and it hits on the splitter, then it is splits into the two halves as shown earlier. See here in pink color, it is split into the two halves. So let me summarize today class. First of all, what is the hydroelectric power potential statistical data we discussed. Second is what is mean by hydraulic turbine has been explained to you, and the difference between hydraulic machine and hydraulic turbine also explained to you. Then the using the layout of the hydroelectric power plant, how the mechanical energy can get by using the turbine. Various components we discussed and the function of each component also has been studied. Then the Pelton wheel is a type of it is a one type of impulse turbine. So what are the various components of the Pelton wheel? We studied, and the function of each component also we discussed. Then the classification of hydraulic turbines also we studied based on the specific speed, based on the head available, based on the orientation of the shaft, based on the direction of the flow, based on the type of energy available at its inlet. We classify turbines into the five types. Okay, so I will stop my class here. Yeah, dear students, I will stop my class here. Thank you for your kind attention. Thank you.